Yeah. Thank you, Ali. Thank you, Hamza, and everybody. Assalamu alaikum. This is Wajahat from Comsets Law Campus. Uh, I hope you can hear me loud and clear. So today, what we'll be discussing, it's more like an introduction to quantum computing for those guys who are like want to have some basic idea that what really is quantum computing all about. And definitely quantum computing is like the future of computing era, and at the same time it's a new computer science. So in order to understand what are the basics of quantum computing, like I would just simply like to request my audience that just simply forget about whatever you know about the computers, because none of those computing concepts are going to be applied today as we speak about quantum computing. Just for the sake of a little flavor of this statement, that when we talk about information or data in computer sciences, it's more like we are talking about something which is logical in nature. But when it comes to quantum computer sciences or quantum computing, the information is no more logical; it's physical. You see, the fundamental construct on which we have been, working on, the entire nature of that construct is changed. So when that nature is no more the same, then it means that the entire computing paradigm is no more the same one. So in order to understand the functioning and the working of these quantum computing or quantum computers, just simply just unlearn what you have learned, and then start writing new concepts over here. So in let's try to build some basic, idea over here, that what are we going to deal with in quantum computing. So there are two basic observations in our life. As you can see in our picture, that in figure B, if I'm throwing some, or we are throwing some balls, and there is a barrier over here, and there are two holes, like we have maybe uh, a hole A over here, maybe, and this is our hole B over here. So it means that either these particles will move from hole A, hole B, or they will bounce back. So there is no possibility that the same ball actually passes through both holes A and B at the same time. That is not possible. So this is a common observation which we see in our real life. And there's another observation when we talk about waves. So, like if you're standing at the bank of a pool, and you are like observing the water waves, how they are moving, and you perform the same experiment, you will see that water waves will be, having such behavior that these waves will be intercepting with each other, and the point where they are intercepting, the energy level will be high as compared to the other part of the waves. As this they touches the wall of the pool, after some period of time, you will see that there is some kind of rusty spectrum over there. So these are two common observations which we see in our daily life. So this is what is the classical view of the things which we experience on our day-to-day basis. Now, what happens when we go into the quantum world? So before touching this quantum world, if someone is not familiar with this quantum word over here, it means that we're talking about atoms and subatomic particles like electrons, protons, nucleus, neutrons, quarks, and unified field. So all those, inner world, down the abstraction of that atomic layer. So when we go into that world, so now assuming this thing, that what happens in that world. So if somehow we are able to extract electrons from those atoms, and we try to perform the same experiment, so what will happen is this, that electrons are more like the particle-like objects, like balls, small balls. And when they are moving, okay, fine, a ball can move from A, from B, as we have discussed. But the interesting part is that we won't be observing this kind of behavior on the wall. Rather, we'll be experiencing wave-like behavior on the wall. No, this is really amazing. That electron was like a particle, or any atom, or whatever you are using as a substrate in this experiment. If it is atomic or subatomic, particle, we will be observing some spectrum, some wave-like behavior. Now, how it is possible? So this is the very fundamental, concept over here, which is going to be the building block of quantum computing. So as mathematically, this is really interesting. Mathematically, it means that one way or the other way, a particular particle was at the two places in same time. And that is something which is not, acceptable for a common mind. So what scientists or the physicists that did is that they started putting detectors over here to observe that when a particle is crossing this barrier or this slit over here, are they having a wave nature or are they having the particle nature? So the interesting part was this, that when the detector was placed over there, so the observation over here was like a particle one instead of a wave-like structure. So this is one another interesting behavior. Then that when we place a detector, the particles are behaving like a particle. When you remove the detector, it means that your particles are behaving like a wave. So from here, the concept was formulated that subatomic particles have dual nature. So they are particle and they have wave. They are both at the same time. So this is something which brings us with two very important concepts in quantum mechanics, which is the fundamental, science of philosophy for building quantum computing and quantum computers. So this very nature of these quantum particles having dual nature or the dualistic, behavior brings us to a very important concept, which is called superposition. So what really is superposition? Something like this. This is the animation, which is simply saying that a quantum particle is a particle and is a wave at the same time. So if like over here, it's a wave and it's a particle, both things at the same time. This is superposition. Now, what really happened is this, that coming back to the point, coming back to that basic assumption that a particle is in two places at the same time, it means that that such existence means that these two counterparts of the same particle are entangled with each other. So this gives us to another concept about entanglement, which means in the universe, regardless of their position in the universe, two components or two particles are entangled with each other. If one particle is representing information state 1, then it means the other one will be representing information state 0. So this is really interesting, that if I toggle this one, which is 1, for instance, then it's assumed that two entangled particles cannot have same state. So according to the law of quantum physics, the other one has to flip to 1. So it means that it's a true parallel processing over here, because we won't be needing iterative processors or loops to go one by one into our a collection of values and try to perform all those computation, because all of these configurations are entangled with each other. Just imagine this thing, that you have one atom which is, or one electron which is representing a 1. So it means that the counterpart of that one which is entangled is representing 0. So if I want to calculate the NOT function on this particular bit or this particular information, so what I'm going to do is that in one round, in one cycle, I'll be computing both things, because all of these values are entangled with each other. So this is really exciting, a very different concept which is not really present in classical computers. Second concept is another one which is really interesting, when we talk about that in quantum computers we don't have information loss. So there is no information loss over here. So what do we mean by information loss, if matter speaking? Like if we simply experience that you have an AND gate. You might have observed that in case of AND gate, what we have this thing that for example, if you have two inputs and one output, if you are giving 1 over here, 0 over here, so you're getting logically 0 at the end. So what does this physically means? That you have 5 volts over here, you have approximately 3.5 volts over here, and at the end you are getting 3.5 volts over here. So the question comes where this particular 5 volt is going. So this 5 volt is basically the information loss which produce heat according to that law of energy. So it means that we are wasting a particular part of information in terms of heat production. So this is information loss we're talking about. So when it comes to quantum computing, we do not suffer these kind of losses because we don't have AND gate, we don't have NOT gate, we don't have all those logical gates, digital logic gates, because in quantum computing we have quantum logic gates. Which the idea of these quantum logic gates is something like this: that if you have a two number of input lines in a particular quantum logic gate, you'll be having two output lines. If you are having three input lines, then it means that you'll be having three output lines. So as the number of input lines are equal to the number of output lines, so which means there is no loss of information over there. So this gives us another interesting concept in quantum computing, which we call reversible computing. Well, in classical computers, apart from NOT gate, all kind of computations are not reversible. So what do we mean by reversible computing? Like if I have a function which is taking x as an input, and you get y as your output. So what do we mean by reversible computing is this: that if we put this y back into this function, then we are expecting that x will be the output. So if you ask a question, you get an answer. Then when you put the answer back into the function, we are expecting to have the question, but what was the query? So this is like a reversible computing. So as you can see that in these classical computing, we don't have this kind of computation which is reversible computability. So in quantum computers, reversible computing is like a day-to-day process over there. So as we are representing information not as a value, in my statement, I never said this thing that a particular atom was representing one as a value. What I referred that there's a state of that particular physical particle which we are referring to as one. For example, like when the electrons are moving, so they're actually moving in terms of spin. So they have half spin. The electron have a half spin, like clockwise, anti-clockwise, clockwise, and anti-clockwise, something like this. So if we assume that this kind of spin is 1 and this is 0, so it means that when the electron is moving, that it means that it is having state 1. When it is moving like this, it is having state 0. So with clockwise and anti-clockwise, representations, we can label them like 1 and 0. So it's the state of that physical particle which we are referring to as 1 or 0. So it means the information is physical over here because they are the states rather than the value of contained in some kind of memory buffer. So there is no value and there is no memory buffer, rather they are the states of those fundamental particles. So this brings us to another very, very important concept. Okay, if information is physical, then can we copy paste those information? Like copy information from here and then paste it over there. That's not possible because there is no cloning theorem. The reason is this: we cannot clone information in quantum computing because information is physical. So in order to clone the information, to move the information from one place to the other place, you need to destroy the information from the first from its source, and then you need to transmit to the target site. So there is no copy paste over here. So connecting the idea of that destroying information from the physical source, from the source, and then transmitting that information to the target source, this is called a quantum communication, which is commonly known as teleportation. So so when we talk about teleportation, it means we are talking about a kind of telecommunication which is based on quantum mechanical and quantum computational aspects, which simply suggests that we can actually transfer information over the communication channel by destroying the information from the source and reconstructing the information on the target side. So these are the very unique features which are unique to quantum computing which this field is offering. So as I mentioned, that quantum computing has a lot to offer, as we can see over here, like superposition, true parallel processing, no information loss, reversible computing, and so on and so forth. So the question comes how this really works, how quantum computing would do what they really do. So from this point of view, to understand all these things, the fundamental algorithmic block over here is something different. Like in classical computers, we have computers as the substrate for computation. So in quantum computing, we have a physical system. So when we use the word physical system, it means those systems which are actually subject to the law of physics. So regardless of all those jargons in physics, the basic process in physics is the law of motion. Even when the electrons are moving, when they are vibrating, when you push some objects, the entire universe. So if you look into the physics, you'll see that there is one common thing over there, that is law of motion. So it means that in quantum computing, instead of doing or regulating the computational process, we regulate motion. And as I was mentioning, that it's all about quantum particles, and every quantum particle, regardless of their abstraction, they are in some kind of vibrating phase. So it means that the motion of the law of motion is over there. So instead of computing, we try to regulate their motion. And the another advantage of this motion thing is this: like, we don't have inputs and outputs. We always have initial state and the final state, or the output state. So it means that if this is my position, right? So if I'm taking 2 steps forward, and if I reverse the magnitude of the same step size, I can go back on my initial phase, the idea of reversibility. So technically, that reversibility phenomena is also due to this law of motion regulation over here. So it means that instead of having inputs and outputs, we'll be having initial state, the output, or the final state. Instead of using computation, we'll be trying to play with the law of motion. So this is how quantum computing, the paradigm is associated with. So how we do it? So first thing is this, that we live as a human being. We are the part of this classical world, where we have either 1 or 0, or any combination of these values. But in case of quantum computers, we don't have 1 or zeros. Rather, we have states, like state 0 or state 1, something like this, which simply suggests that the quantum world is a superposition of 0 and 1. So in simple words, what really is superposition? It is a linear combination of all possible values. So it means that all possible combinations which are lying between 0 and 1 are already in this quantum world. So what we do is that from classical world, we simply give information as we deal with in zeros and ones. Once those informations are in that quantum computers, they are switched to superposition, which means that they are the representation of all possible states. And once we get the output, the final state, we collapse. I'm using a very specific word, and I'll explain what do we mean by the word collapse over here. So we collapse the quantum world and get our classical output in terms of 0 and 1, or whatever their decimal number or character representation is. So it means that we don't know. This is the real oracle, or this is the real black box over here, the quantum world. We don't know what's really happening over there, because we have all possibilities being computed at the same time. Okay, let me put it something like this, that just imagine that you have an 8-bit quantum register. So what do we mean by a 8-bit quantum register? It means that 2 to the power 8 means that we have 256 possibilities. So when I'm saying that the quantum register, 8-bit quantum register, is in the superposition, it means that in this quantum world, we have 256 possibilities at the same time. So it means the entire configuration of the quantum world contains both the question and the answer at the same time. So all I have to do, instead of computing it, I have to curate, because the answer is already over there, assuming that there is no overflow or buffer overload. So, but there is a catch also. Quantum world is very sensitive to all those cosmic radiations. So it means that this superposition collapse randomly due to the effect of those cosmic radiations. So in quantum computers, the people are trying to isolate the quantum computer or the quantum world or the quantum processors from those cosmic radiations, so that a random collapse may not occur. So this is one of the limitation which we are facing right now. That's why I used the word collapse before. So if everything is going as to our desire, so what really happens is that when we are running a quantum algorithm, as the quantum algorithm completes, that ends. So that quantum algorithm, after at the it's at the end phase, it collapses the quantum world intentionally, so that we can get the classical information 0 or 1 or any number which is understandable by by the human beings. So whatever I've been saying till now is like a quantum bit. The mathematical representation is something like this: that a bit over here is some kind of this representation, like over A, and this B or alpha or beta over here. Beta is like the computational basis, like the probability that your quantum bit is in state 1, the probability that your quantum bit in state 0. So this is called, this is the superposition representation of a quantum bit. But the point over here is that this alpha and this beta or A or B over here belongs to the complex domain. So this is not the right time to reason that why it is in the real domain, why it is not in the real domain, rather it's in the complex domain. So the every computing over here is in the complex domain. So if you're not familiar with the word complex domain, it means that something like this, that we're not talking about simple numbers, rather we're talking about something like this, that x plus iota y. Over here, this iota is that imaginary thing, which is like the under root of -1. So states representation in your quantum computing regime, it means that the probability amplitude, which is like according to this calculation, must be equal to 1. So if your if probability amplitudes are not equal to 1, it means that there is something wrong with this quantum bit representation. So mathematically it's a matrix, in a real world domain, sorry, in the complex domain. So this is state 0 and this is state 1. So this is a matrix representation of state 0, and this is the matrix representation for state 1. And more idealistic speaking, this is alpha over here. So it means that this is going to be the alpha, which means alpha is that computational basis. So generally speaking, whenever we are trying to increase number of quantum bits in terms of quantum registers, so if we have 2 quantum bits, so their representation will be the as the tensor product of quantum bit A and quantum bit B. So that is mathematically something like this. So this is how the quantum registers are being formulated. You see, there is no Boolean algebra anymore. And so the algebra for quantum computing is your linear algebra in complex domain, in which we'll be talking about dual vectors, we'll be talking about tensor product, and so on and so forth. So just to give an idea that what kind of gates we're talking about. So as I mentioned that we don't have those classical AND gates and OR gates. So the fundamental gate over here is called C0, control not gate, something like this. We have a quantum state A, we have a quantum state B. The quantum logic table is something like this, that if we combine these two states, 0, 0, for example, so we'll get 0, 0. If we have 0, 1, we'll get 0, 1, and something like this. And this is the diagram of that notation for this C0 gate. So what really happens over here is simply like this, that if we have 1 over here, it means that this particular gate gets enabled. So whatever the input is being represented in the state B, the XOR of A and B will be the output of this one. So this is how the C0 gate is being, represented. Mathematically, it's a matrix, something like this. So it means that a matrix is technically a gate over here. It's an operator over here also at the same time, because these gates are operators which are applying on operand A and B in their quantum states. So this is another gate which is really interesting one. If as I mentioned that in my preview over here, that we give inputs in terms of classical inputs, and they are translated into their quantum world. So what really happen over here is that if in your classical computers you are representing 1, so as soon as it's entering in this quantum world, this will be in its pure state, which is something like this. And as soon as it comes over here, a gate called Hadamard gate will be applied on this state 1, which will convert this information into its superposition state. So this Hadamard gate is the superposition based representation for all coming inputs. So so there's another one which is a Toffoli gate. So for instance, if someone desperately needs to apply AND operation or NAND operation or something like that, so we can use Toffoli gate, something like this, that we can fix the values of this A and B, and we can, forcefully ask the Toffoli gate to act as an AND gate or NAND gate, and then we can actually perform all those, activities. So this is just to give a flavor or the idea that we are using linear algebra over here. Each matrix is the representation of a quantum gate. We have number of quantum gates over here. Each gate have their own quantum logic, tables. So an ordinary, a normal quantum circuit is something like this, that we have a Hadamard gate, we have a Hadamard gate, this is Poly-X gate. So combination of all these gates are giving some inputs and some outputs. So this is how a quantum gate looks like, rather than the transistors are over there and capacitors are over there. So in quantum world, we don't have capacitors or transistors at a conceptual level of circuit designing. Rather, we are talking about all those quantum processes which are simply matrices over here. So when we talk about applications, that why to bother all those things? So these are some very exciting application areas where quantum computing is playing an amazing role. Like first one is the teleportation. Okay, before moving into this one, to understand, taking into account all those complexities which I've shared with you, which is just an introduction to quantum computing, by the way. So why to bother? Okay, let's simply consider this thing, that I have a number. This is the example from a very popular quantum computing textbook, like 26. So it means that we have a 2-digit number. Now consider this, that I have a number with 300 digits, for example. So if let's assume this, that I have a number with 300 digits, and I want to factorize this particular problem on a computer system with 1 terahertz speed. Just imagine that how much time will be required to solve this problem. So according to this textbook example, a 1 terahertz computing machine will take approximately 150,000 years. And if we have in the right configuration of a quantum computer oscillating at 1 terahertz, that will take less than 1 second. So you can see the computing power of quantum computing. Yet, yes, we have not yet reached its, quantum computing has not yet reached its full potential at this time. So we have to acknowledge, because there are so much, physics and all those constraints from the law of physics are over there, which are like acting as a barrier or as a fiction in the progress. But still, we have very encouraging results. Number one. Number two, keeping in view that we have this superposition thing. So it means that if we have all possibilities at the same time, now imagine if we have an encryption of 512 bits, So if we want to crack it, what will happen? We simply ask a 512 quantum bit computer system to crack it down. So according to Boeing, I was reading one article from Boeing. So according to them, the current state of the art in quantum computing will take 15 minutes to break any kind of latest encryption models, because they already knew the answer for your questions. So that is the strength or the power of this quantum computing, which is once again the red alarm over here. So as I was saying there about teleportation or telecommunication, so China has already experimented on teleporting few quantum particles over between Beijing and Atlantic, and they have already launched approximately 1,400 quantum satellites at their 500 kilometer altitude. So this is the experiment which was done by China in 2016. So you can imagine in last 4 years what kind of progress they have been made. So one can easily expect that maybe after 20 years or 30 years, I might be emailing a sandwich made by me through email. So and you will be receiving my sandwich as an attachment due to this result of quantum teleportation. So this is like the thing which we're expecting. So at this time we are able to not physically teleport objects, but rather few atomic blocks or quantum particles. Let's give some time more to the technology. As we don't have no cloning theorem, so money forgery and all those things, the next upcoming money paradigm is quantum money, quantum software protection. One of the bottleneck, as Bishop was already sharing the idea of the computing complexity which we are facing in deep learning models and all those things. So with the power of two pair processing over here and those superposition and entanglement, quantum AI is going to reborn, because now we might be having, it is like assumption over here, with all those strength of quantum computing which has to offer. Once we are there at the level of more full-scale quantum computers, we might be able to do a lot of in artificial intelligence. And this brings us to the development of quantum robots, quantum cognition. Quantum OS is already on the way. Quantum C++ has already been developed. You see, it's entirely a new playground for us to play once we are able to understand how to handle those quantum mechanics and all those these concepts. So this is like a simple picture of how a quantum processor looks like. And this is the system unit of quantum computer by D-Wave, one of the coolest place on planet Earth. What we have been doing for last couple of years, we have tried to develop, in my research group, we have written our own quantum simulators. We have developed a quantum cognitive architecture. So our quantum simulator can simulate 13 quantum bits on your standard laptops or PCs. And with the help of those things, we have developed an AI system which is able to dream. So I normally share this particular video in which we have a 10-second dream. So we are looking for collaborators in this field. So anyone can join us. This GitHub downlink is for our quantum computing framework, which was written in C#.NET. And by the end of this week, I'm also launching my quantum computing tutorial for beginners. This is the link. I'll be sharing my slides after this talk. You just simply click this channel and you can start learning quantum computing from next week. Inshallah. Thank you very much. Jazakallah. So if there are any questions or anything where I can help, please do let me know.
Dr. Saab, I have a question, if you don't mind.
Please.
First of all, this was very, informative and very wonderful presentation, and I love that idea of teleporting the sandwiches. Me as a foodie would be amazed and would be in love with this thing. Sir, you talked about the two-way directional movement of information in quantum computing. Is it similar to the control feedback system? If it is so, then what about the applications of control feedback? Would quantum computing be replacing all the control feedback applications like ABS brake, industrial control motors, and all other control feedback linked application? Number two, yes, that one is that you, said in your presentation that the information is destroyed from the receiver's sender's end, then it is sent to another end. Then that means that quantum computing would play a pivotal role in the security of information.
Yes, yes.
And
Okay,
third, please.
let me answer. Okay, well, I'll start with the question number 2 first, right?
Okay.
Yes, I totally agree with you. Okay, obviously there are always, way out. When I said that in case of entanglement, if we have 1 over here and 0 over here, so these two cannot have same states over here. So there is another concept in quantum computing which is called Bell state. So in Bell state, we can have both, counterparts as 1 or both counterparts as 0. So this is a very rare state which we forcefully put on those quantum particles, which is actually used in teleportation. Number 1. Number 2, yes, the idea of quantum communication or quantum encryption is like to enhance the security as well, because the entire infrastructure is black box. So when you try to steal the information from that oracle is a standard word for quantum processors. So when you will steal the information from processor, the oracle, the entire quantum computational configuration collapse. So when it collapses, it means that end of the game. You won't be having that quantum information anymore. So that could be if the collapse is wrong, it means that you might be getting false information. So it means that the oracle is or the quantum world is too much secure as compared to we witness today. And regarding your first part of the question, when we talk about feedback, so if I'm wrong, please correct me. In case of feedbacks, what we are saying that the system is generating an output, and then output is being evaluated. And that evaluation, the difference between the expected and the output is the feedback, right? So when we said reversible computing, it's not the feedback, basically, it is the actual output. So, it's not. And the second part of your first question regarding the replacement of the control system and all those things, one thing is for sure, keeping in view the complexity and all those things which quantum computing has to offer. One thing is pretty much sure that quantum computing would not be replacing our day-to-day computing. Rather, quantum computing will be the tools which will be doing all those kind of activities and helping us to solve those problems which are yet not possible with these classical computers. Maybe after 70, 80, or 100 years, quantum computing might be at the desktop of every northern person, but as far as the complexity and all those things of quantum computing are considered, I'm not sure that we'll be doing all those day-to-day work over here on quantum computers. Yeah.
Thank you.
I hope I answered the question. Yeah.
Yes. Thank you very much.
We have one question from Saad. Is that
Yes,
what are your views on the privacy violation due to the quantum computing, as you said that it would take only 15 minutes to decrypt any kind of encryption?
Yeah, this was a statement given in the article which was published by Boeing on their quantum computers. Yes, this is like the alarming condition for everybody in the world. So that is why, first of all, like third world countries are not very much, welcome in doing quantum computing on those areas. There are just few people who have done, like Dr. Sabi Anwar is one of the graduates of, Oxford University, who have his PhD in quantum information, etc. So there are very small number of people who are doing, getting all those technologies from there. So these are the major concerns. Even the Western countries, all those, they have this question mark over there. in the progress of quantum computing, because nothing will be